Okay, so now we're going to be looking at the cross product. The cross product will be really important when we start looking at torque. Then we'll be using the cross product quite a bit. But just like with the dot product, this is just an introduction. So as I said before, the cross product results in a vector. So we're going to multiply two vectors together, and we get a vector back. And what's really cool about the cross product is it returns a vector that is perpendicular to both of the individual vectors. Or in other words, it's perpendicular to the plane that was determined by the two initial vectors. And we can think about that in terms of, we've got two vectors on some table here, A and B, and the resultant vector is going to be perpendicular to both, so it would be coming straight out of the table. What we have here, these pictures are showing a depiction. Here's one, and here's a next, of something called the right-hand rule. And the right-hand rule is the way in which we can determine the direction of the resultant vector. And the way that it works is you put your right hand, if we're talking about A cross B, which is what we're looking at in this top one, you put your right hand in line pointing in the direction of A. That's here. And then what we're going to do is you're going to curl your fingers in the acute angle toward B. And the result is your thumb pointing in the direction of your new vector, where this is showing the vector coming out of the table, the vector C. So we've got a vector coming out. In the bottom example, we're looking at B cross A. And so same two vectors, only now we put our right hand sort of flat on B, and we are going to curl our fingers in the direction of A in that acute angle, the smallest angle between them. And the result is our thumb pointing in the direction of the vector perpendicular to both. So we'll call this vector D. Well, really important, how do vector D and C relate? Quite clearly, C and D are in exact opposite directions. And so right away, we're given an important understanding, which is that in the cross products, the multiplication is not commutative. Or in other words, A cross B does not equal B cross A. They're very similar, but they're in exact opposite directions. All right, well, let's think about what the magnitude of a cross product looks at. So imagine we have vector A here and vector B here. Whereas the dot product is looking at how much of each vector, is looking at the vectors in the same direction of one another. The cross product is looking at the size of the vectors that are not in the same direction as one another. So the further the vectors are from one another in terms of the angle, the greater the cross product is going to be. So if we call this angle theta, A cross B is looking at how much of A, it's looking at the magnitude of A that is perpendicular to B times B. So the magnitude of this is magnitude of A times the magnitude of B times sine of theta. So it's looking at the magnitude of A that's not in the direction of B, that's perpendicular to B, times the magnitude of B. So pictorially, what we're talking about is, here's A perpendicular to B, we're multiplying, you know, the magnitude of this vector times the magnitude of that vector. And what's critical is that, if we have two vectors, A and B, that we're always looking at the acute angle between them, or the smaller angle between them. So if it looked like this, A and B, the angle that we'd use is that angle right there. Okay, well let's dive more into cross products. So let's think about our unit vectors. So we have I dot I, or I cross I. Well, I cross I, here's I and here's our other I. What's the angle between them? Well, the angle between them is 0. So I cross I is going to equal the magnitude of I times the magnitude of I, and both of those are 1, times sine of 0. So 1 times 1 times 0, 0. Similarly, each one of these, because they're in the same direction as one another, will result in 0. What that implies is that when you cross two vectors and it equals 0, it says that they have no component values that are perpendicular to one another. If a cross product equals 0, it shows that the vectors are parallel. All right, well, what about if we cross I with J or I with K or any of them? So if we have, I crossed with J, put your right hand in the I and curl your fingers up towards J, and the resultant vector is K. And that makes sense because the resultant vector needs to be perpendicular to both I and J, and the vector that is perpendicular to I and J is K. And it makes sense that I cross J in terms of magnitude is going to be 1 magnitude of I times 1 magnitude of J times sine of a 90-degree angle between them, which is 1. So it makes sense that the magnitude is 1, and the magnitude of K we know is 1. What about J cross K? Well, that's, put your hand in the J direction. And curl it towards the Z direction. So have your fingers curling towards K, so in the Z direction. And what you get is a resultant vector coming out in the X direction. Or rather, we get the unit vector I back. Okay, let's keep looking at some more of these. What about if we cross I with K? So try to think about what that is. Put your hand on I, curl it towards K. And what you should get is a little vector coming down, and that vector being negative J. Well, so we did IJ, JK, IK. That's good enough. So you get the idea that when you're crossing unit vectors I, J, and K, I and J, it's going to get you K. Well, maybe let's just do one more. What if we did J cross I? So we're crossing J with I. So again, put your hand in the J direction, curl it towards the X direction, and what you're going to get is a vector going into the board, and that vector would be negative K. All right, well, let's think about putting this all together now to look at the most complete way of doing a cross product. So if we're crossing, A cross B, and we're looking at their components, what we can do is we can write this using distributive laws as AX, BX, I cross I, plus AX, BY, I cross J, plus AX, BZ, I cross K. So that's the top, plus AYBX, J cross I, plus AYBY, J cross J, plus AYBZ, J cross K. And lastly, AZ, BX, K cross I, plus AZ, BY, K cross J, plus AZ, BZ, K cross K. Let's go ahead and get rid of the 0. So we know that I cross I is 0, and J cross J is 0, and K cross K is 0. And then let's go term for term here. So that turns out to be AX, BY, I cross J is K, plus AX, BZ, and I cross K is negative J. Plus this term, AYBX, J cross I is negative K, plus AYBZ times I, and let's keep going just a little bit more. So now we've done that one. So plus AZ, BX, K cross I is negative J, plus AZ, BY, and K cross J is negative I. Okay, so let's take a minute to breathe here and digest this. All right, great. So I had to stop because I realized I made a little mistake. This term here should have resulted in a positive J. So this value here is positive. So then we can collect all these terms, and what we get is AYBZ minus AZBY I. So combining those and rewriting, instead of having negative I, just putting the negative out in front, because we know that adding vectors, adding a negative vector is the same as subtracting the vector. And then we look at plus AXBY minus AYBX K. Maybe I should have written the J's first, but that's good enough right now. Usually you write IJK, but I wrote the K's first. And then the J terms. So the J terms would be plus AZBX minus AXBZJ. And so this gives me, you know, it's terribly ugly, but it's looking at the two components, or sorry, it's looking at the components of vector A and vector B, and it's giving me the vector that is the cross product to those vectors A and B. So this vector that I just found is perpendicular to both A and B. This has a huge amount of implications in both physics and in multivariable calculus. This will be huge as well. But let's recognize that, wow, this was a tedious process to get to this vector. So I'm going to show you, without a whole lot of proof, a way of using what's called a matrix and a determinant to do cross products really rather quickly. So let's say that we have, and I'm going to use actual numbers so you just see some numbers. Vector A being, you know, let's say 1i plus 2j plus k, and vector B equaling 2i plus 3j minus k. And I want to find A cross B. The method here is that we write a matrix as in the top we're going to have I, J, and K. And then the next row are the A coefficients. So we have 1, 2, and 1. 1, 2, and 1. And then the next line is my B. So 2, 3, and negative 1. And the process goes like this. The first thing that we're going to do is we're going to kind of cover the first column. And we're going to multiply across. So we're going to have 2 times negative 1 minus 3 times 1. And since we covered the first column, that's the I. So that's I. Plus, well, here's the one thing. So it's this kind of strange pattern of plus, minus, plus, minus. So it's actually minus, and now we're going to do the same thing. So now we're going to cover up the J term, and we're going to do 1 times minus 1, so, and then minus going across the other way, 2 times 1. J. And then plus, and so now we're going to cover up the K column and multiply across. So 1 times 3 minus 2 times 2 K. And this is our vector that is the resultant cross product of A cross B. So it's a vector that is perpendicular to both A and B. And if we simplify it, we get negative 5i minus negative 3j minus k, which can be simplified further to minus 5i plus 3j minus k. Last and not least, I want to show you one more nice method for doing cross products. So hold on one sec. Okay, so the last thing here, I just Googled cross product calculator, and there are tons of these free software that can calculate, that can do cross product. So this one here is analyzemath.com / you can read. But the way it works is you can just enter in a vector. So let's call vector u, and we don't need to put the i's and k's. So let's say it's like, you know, 2i, 5j plus 9k, and vector v, let's say is negative 1 plus negative 1i plus 3j plus 9k, 4k, and then just press enter, and it will give you that cross product really quickly. So it's negative 7i minus 17j plus 11k. So this is a nice way for you to check your work and recognizing that cross products are a little bit tedious. Cool. So that's it. These two videos looked at multiplying two vectors. The first one was dot product, where the result was a scalar, and it was looking at vectors and concerned with vectors in the same direction as one another. And then the second case was cross products, which resulted in a vector, and this was looking at the resulting vector being perpendicular to both the initial vectors. So there we are.